Alright, so today we're going to be looking at problem 4.15. So, we are given, the question asks, if we have a thick spherical shell that has polarization P pointing radially outwards, except it's hollow in the middle. They give us the polarization. It asks us to solve for the field using both Gauss's law as well as using electric displacement. So to begin with, for Gauss's law, for R is less than A, we can tell that inside it's a hollow shell. So inside, the Q enclosed is going to be 0. And looking at Gauss's law right up here, we can see that if Q enclosed is 0, the left side also has to be 0. Therefore, the electric field has to be 0. We can use the same logic for R is greater than B, so outside the sphere. And the field is again going to be 0 everywhere else. When we look at inside the shell, however, the thickness, Q enclosed is not going to be 0. So if we use Gauss's law, and some algebra, we can actually solve. We can pull E out of the equation here because it's going to be constant. So we have the electric field times the area is going to equal Q enclosed over epsilon naught. As we can see here, the area is just going to be 4 pi r squared. So we have epsilon naught times the field times 4 pi r squared is going to be the enclosed charge. Moving down here, some more simplification. For E, if we plug in the polarization over epsilon naught, we will find that using this equation for the polarization up here, the epsilon naughts will cancel, and we will have the polarization, negative polarization times the area, which is going to leave us, after simplifying, which is going to leave us with negative k times 4 pi r. Plugging that back into Gauss's formula, or Gauss's law, excuse me, we can simplify further to see that the electric field is going to be negative k over epsilon naught times r hat. Now, using the electric displacement, it's going to be similar concept for inside the shell and outside the shell. The problem does actually state that there are no free electrons in the diagram here. So when we're looking at the electric displacement, we can set Q of free electrons enclosed to be 0 for both inside the shell, so R is less than A, as well as everywhere else, or R is greater than B. Next we have here, so we'll have the integral is going to be set to equal 0. So again, similar to before, the magnetic field is also going to be 0 inside the shell and outside. So we'll have splitting up the electric displacement into its components, the field and the field and the polarization. They're going to be 0. We know that P is going to be 0 right here. Therefore, the field also has to be 0, and that checks out with before. However, when we're looking at the interior of the shell, not the middle, but the in between the shell, we'll find that the polarization we can just again set to this formula up here, and we will find that after a little bit of simplification, we will find that the field is going to be equal to the negative polarization over epsilon naught, which is going to simplify to negative k over epsilon naught times r hat, which again checks out with our previous answer.